Hello, Math 111 students, and welcome to our new section, Chapter 5, and we're going to start with quadratic functions. So our learning objectives for this section are to recognize characteristics of quadratics, understand how the graph of a parabolic shape is related to quadratic functions, determine a quadratic function's minimum or maximum value, and solve problems involving a quadratic function's minimum or maximum value. And these are just some nice pictures of quadratics, or parabolas that I stole from somebody else. Kind of see them all over your world. All right, so let's practice identifying characteristics of a parabolic shape. So here is a graph of a quadratic function, and it has a couple different characteristics that you need to be able to identify. So to start with, I might try, no, I don't think I'm going to try highlighting, I'm just use a green pen. All right, so the first thing you can recognize is that it's a U shape or a smiley face, and one thing that it is that it is symmetric, and it is symmetric about its axis of symmetry. The axis of symmetry is a vertical line indicated by the red dashed line that if you folded the function on, like if you could fold my screen in half on that line, the left side would match up with the right, and that's what it means to be symmetric. That line right there is the axis of symmetry. Now remember the equation for vertical lines. It's x equals a value. This one is occurring at 1, so the axis of symmetry for this example is x equals 1. And that's how you write the vertical line. So you have to be careful. This is a time when context is really important in mathematics. X equal 1 could look like to a solution to an equation. Or in this context, since we're talking about graphs and parabolas, x equals 1 is a vertical line, equation of a vertical line. The vertical line that is the axis of symmetry. All right, the next thing we notice is that it has a vertex. That's going to either be a maximum or a minimum value depending on if the parabola opens up, then it's a minimum, it's at the bottom of your valley, or maximum if it's a mountain, if it opens down. This vertex is an, oops, I didn't mean to do that, is an ordered pair in the plane, and it occurs at, sorry about that, well, it's over 1 down 4. So the vertex occurs at the point 1, x equal to 1, y equal to -4. Now you'll notice that the x value of the vertex is always going to be the same as where the axis of symmetry falls, because the vertex always goes through the axis of symmetry. Because there's only one vertex, only one minimum in this example, so it must go through the axis of symmetry. So these guys are always going to be the same value. The x value in the vertex and the x equal value on the axis of symmetry are always going to be the same value. All right, two more things to notice about the parabola. There's always going to be one y-intercept, and this y-intercept occurs at the point over 0, always over 0, because the y-intercept is where it crosses the y-axis, so it's neither left nor right. It's always at x equal to 0, and the y value in this is -3. So for your y-intercept, this value will always be the 0 because we're neither left or right, right? We're right at the y-axis. Right at the y-axis. And the last characteristic that we want to talk about are the x-intercepts. Now you're not always guaranteed 2 x-intercepts. You could have 2 x-intercepts, you could have 1 x-intercept, or you could have no x-intercepts. And we're going to talk about that a little bit more, just depending on how the quadratic function behaves and on how the parabola falls on the graph. In this example, we have 2 x-intercepts. The first one's at -1, 0. And the other one is at 3, 0. And with x-intercepts, similarly with y-intercepts, that y value is always going to be a 0 for x-intercepts because you're not up or down. You're sitting right on the x-axis. All right, so these are the features of the parabola that goes along with the graph of a quadratic function. There's an axis of symmetry, there's a vertex, there's always a y-intercept, and there could be 2, 1, or 0 x-intercepts. All right, let's practice identifying these guys. All right, here's a graph we're going to look at, and we're going to label all the things we just learned about on this graph. All right, so let's start with the top. Is this going to be a max or a min? Well, I can find the vertex right here, right? And the vertex is, in this case, it's a mountain, right? So this is a maximum vertex. It's a max. And it occurs at -1, 4. I can just read that right off the graph. And so that's my vertex. What about my axis of symmetry? Well, remember that runs right through the vertex. Here's my axis of symmetry. I'm going to draw it in. And that's going to be at x equals -1. Always x equal to the x coordinate of the vertex. All right, so I found my vertex, I found my axis of symmetry, my horizontal intercepts. Now these on this one, I can label them, but I can't exactly find them because I can estimate them. I can estimate them, but I can't find their exact value because they don't fall in a nice grid point. I'm going to estimate these. I'm going to say this one's about 1.80, and this one estimate about -3.80. I can't find them exactly from this graph because it's just not zoomed in enough or accurate enough. And the vertical intercept, again, this one I think I have a better guess at. To me, that looks like over 0, up 3.5. It's a pretty good guess. I think that one's right. All right, so that's how we identify key features of a parabola. Let's talk about the domain and range of quadratic functions before we jump right into them. Oh, I didn't tell you what a quadratic function was. Well, I'll say it right now. Quadratic functions look like f of x equals ax squared plus bx plus c. I meant to have that in there. That's okay, I can write it in. That's what quadratic functions looks like, and the quadratic is always in that. That's a standard form of a quadratic function. I'm saying the wrong words here because your book uses different. So anyway, that's what do we call those? Hang on. General form. That's the general form of a quadratic function. This is the general form of a quadratic function. And you can, when we go to figure out the domain, we can look at this equation. And we looked at a couple graphs, so we have some ideas about domain. And remember, when you're checking domain of functions, there's two things that can go wrong. You can divide by 0, but you can see that there's no division sign in the quadratic function, so that's no problem. No problem, no dividing by 0. And there's not a square root symbol, so we're not doing any square rooting, right? So we don't have to worry about taking the square root of negative numbers, so that's no problem, which makes the domain of all quadratic functions minus infinity to infinity. Another way to say that, all real numbers. Okay, there's no problems with the domain because you're not going to divide by 0 anytime because you're not dividing, and you're not going to square root a negative number. So let's talk about the range. Well, the range depends on the vertex. If you have a vertex that's a minimum, a valley, your range is going to be from the vertex, right? That's your lowest possible value on up to infinity. Okay, so this value looks like it happens at -3. So for this example, my range, my range starts at -3 and goes all the way to infinity. That was my range. I should write range. Domain all real numbers range from -3 to infinity. However, if you have a parabola that opens down, looks like a mountain, then you have a local maximum. So your ranges go from -infinity up to that value. Well, this looks like it's about at -2, 5. So in this case, my range goes all the way from -infinity up to -2, and that's where it stops. That's my maximum. So my range is -infinity to 5. Right? So finding the domain and range of quadratics isn't too bad. The domain, remember, all real numbers, and the range depends on if it's an opening up quadratic or an opening down quadratic. All right, that's it for video 1.